Algebra 1, Lesson 107, we are looking at our absolute value functions, but we are going to be able to graph them today. So let's first look at our parent function. Just like we have parent functions for our linear equations of f of x equals x, or our quadratic equations, f of x equals x squared, our absolute value function has a parent function that is f of x equals the absolute value of x. This is the most simple, and from here we can do lots of translations, we can do stretches, compressions, you name it. Okay, so let's just look at what our regular parent function looks like. So we're going to plug in some different values here for x. We want to get a few of them. So maybe I go from -3 to 3 on what I choose. So let's see if my pen is going to work here. Just be patient with me. All right, so if I have -3, -2, -1, and then we have 0, 1, 2, and 3. Well, when we plug all of these in, if I were to plug in f of x equals the absolute value of x for each of these, we would end up with 3, 2, 1, 0, and then another 1, 2, 3. Which means when we go ahead and graph this, I will have a point here, 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 here. So we see that negative slope, and then we start going up again. We have this positive slope, okay? And you can see how we can continue the pattern up and out. This is our parent function. Looks very different from anything that we've had before. These absolute value functions will always create this V shape, and it's not curved like a quadratic function. It is, does have that corner to it. And so from here we can do lots of different transformations. But a couple questions. What shape did the graph create? Well, that's a V. Where was the vertex? Well, the vertex is, remember, where we stop decreasing and start increasing. That means our vertex is where this corner is. It's at 0, 0. Okay, we call that point of symmetry or the corner. It's the vertex of the absolute value function. And these graphs have two slopes, one negative, one positive. What are the two slopes of the parent function? Well, if we look back at the slopes here, we would say this one is a -1 as a slope, and this one is a +1 slope. Okay, so -1 when we're decreasing, and +1 when we're increasing. So let's see what happens if we were to change our function just a little bit. So if we add outside the absolute value bars, the graph will either go up or down on the coordinate plane. So adding this k here on the outside is a vertical translation. And we can say if k is greater than 0, so a positive number, the graph goes up, okay, just like we would imagine. And the graph goes down when k is less than 0. And we can always say that the vertex is at that 0, k. All right, so let's look at f of x equals the absolute value of x plus 1. We're still going to plug in -3, -2, -1, 0, 1, 2, and 3. We can pick lots of different possibilities, but just for the sake of ease, let's just pick these ones. So when I plug in the absolute value of 3 plus 1, we get 4. Absolute value of -2 plus 1 is 3. Absolute value of -1 plus 1 is 2, 1, and then we start going up again, 2, 3, and 4. Which means when I go to graph this, I have my vertex now at 0, 1, and I have my points on either side here. We still have that slope of 1, but now our vertex is not at the origin, it is at this 0, 1 because of this +1 on the outside of the absolute value function. Okay? So similarly, if I had something like f of x equals the absolute value of x minus 2, we would say that the vertex is at now 0, -2. We've moved it down twice, which means I haven't changed the slope of either line, and we could graph it pretty easily just by saying these are the points that I have. And you can confirm that by plugging in different points if you would like. But all I have done with that f of x equals the absolute value of x minus 2 is move it down twice. Okay? Now, what if we have subtraction or addition inside of the parentheses or inside of the absolute value bars? Well, if we subtract inside the absolute value bars, the graph will either go to the right or the left. So instead of a vertical translation, we have a horizontal translation. Now, this one's a little bit more, little bit counterintuitive, kind of. The biggest thing is that we have to remember that this is subtraction inside. So if that h value is greater than 0, okay, so I'm subtracting a positive number, it goes to the right. If we are subtracting a negative number, okay, it's going to go to the left. And our vertex is now at h comma 0. Okay, remember that the other one that we just did, a vertical translation, is at 0 comma k. This vertex, when we just changed to the right or the left, is now h comma 0. So we could already say for this, our vertex should be at 1 comma 0. Well, let's prove that with some numbers here. We're going to pick -3, -2, -1, 0, 1, 2, and 3. And we plug it in. We have to be careful here. So if I have the absolute value of -3 minus 1, that means I have the absolute value of -4, so I get 4. Absolute value of 2 minus 1 is going to be a -3, so we get 3. Absolute value of 1 minus 1 is a -2, so we get 2. If I have the absolute value of 0 minus 1, I get -1, the absolute value of -1, which is 1. If I have 1 minus 1 inside there, I will end up with the absolute value of 0, which is 0. 2 minus 1, okay, we get 1, and 3, we get 2. And we're going to see that it starts going up at that point. So if I plot this, -3, 4, -2, 3, -1, 2, 0, 1, and 1, 0, 2, 1, 3, 2, and we could continue this pattern. And we can see that just by plugging in and seeing where those plots put us, we see that it has shifted to the right once. Okay, so that subtraction inside, if we are subtracting a positive number, we go to the right. If we are subtracting a negative number, we go to the left. Now be careful, if we are subtracting a negative, it will look like a plus. Okay, so just like this one. So if I have f of x equals the absolute value of x minus a -1, you are going to see this as actually f of x equals the absolute value of x plus 1. Okay, we are subtracting a negative, meaning that we're going to be going to the left, and our vertex is now going to be at -1 comma 0. Okay, now once again, the slope hasn't changed, and you can prove this by plugging in points, but our points should be along just like this. Okay, it has shifted to the left once with that subtraction of -1. Okay, now if we put them together, if I have something subtracted on the inside and added to the outside, okay, we can combine both of these. Now, from what I know about the vertex, I can say, well, I know that that inside is going to change my x coordinate of my vertex. So if I'm subtracting 4, that means that I've moved it to the right 4. Okay, and that plus 1, I've moved it up 1, which means that my vertex is actually at 4, 1. And we can prove that by plugging in lots of numbers. Let's say we plug in -1, 0, 1, 2, 3, 4, and let's say 5. If I plug in -1, I will end up with -1, absolute value of -1 minus 4 plus 1. Okay, that means that I have absolute value of 5, -5 plus 1. So 5 plus 1 is 6. So I should be -1 and up 6 right here. Okay, plug in 0. Okay, 0 minus 4, absolute value of that is 4 plus 1 is 5. Plug in 1. 1 minus 4 is -3. Take the absolute value is 3 plus 1 is 4. Okay, we can start seeing the pattern here. All right, and we could see it start going, oops, sorry, this shouldn't have been a 0. Sorry about that. If I plug in 5, I get absolute value of 5 minus 4, which is 1, plus 1 is 2. Okay, so we start seeing it go up again, and the 6 is going to be a 3. Okay, so if I do this, I have 0, 5, 1, 4, 2, 3, 3, 2, 4, 1, and then we start going back up again. All right. Once again, the slope has not changed. We have not changed that part yet. We have just done some vertical and horizontal transformations. Okay, now if we start changing the slope, this is what it's going to look like. Just like any other parent function, we can multiply by a constant, and the graph will end up being stretched, reflected, or compressed. So some rules for you. If a is less than 0, so if our constant is less than 0, that creates a reflection. If we have a negative constant, it's going to be a reflection, just like what we've seen in many of our other functions. Now, if the absolute value of a is greater than 1, so if we're looking at a 2, 3, 4, 5, or even a -2, -3, -4, -5, we are going to be stretching. Okay, once again, just like we have with any of our other parent functions. And if it's less than 1, we are going to compress. So if we have a fraction, a smaller number, it's going to be compressing our function. Remember, that's getting it closer and closer to that x-axis. So let's say we have 3 times the absolute value of x, and we want to graph that. Well, our a is equal to 3, which means that we have a stretch here. Now, we haven't changed this horizontally or vertically or anything like that, which means our vertex is still going to be at 0, 0. But let's plug in some numbers to prove that. All right, so if I plug in -3, 3 times the absolute value of -3 is going to be 9. 3 times the absolute value of -2 is 6. And then we have 3, 0, 3, 6, 9. All right, so we can plot all of these. All right, and you can see that axis of symmetry here really clearly. All right, and we have my absolute value function. You can see how instead of being a little bit wider spread, this is stretching up. And instead of having a slope of 1 for each of those, or -1, we end up having a slope of -3 and +3. And that comes from that constant on the outside. So for this one, if I had f of x equals -0.2 times the absolute value of x, well, -0.2, not only is it negative, so we are going to have a reflection, but it is less than 1, which means we are going to have a compression. Okay, so let's prove that. So let's say I plug in, I'm just going to do a couple here. If I do -3, we'll just do the whole thing. -1, 0, 1, 2, and 3. These are not going to be super nice numbers. That's okay. Okay. If we plug in -3, we are going to have -0.2 times the absolute value of -3, which means we have -0.2 times 3, which gives us a -0.6. So a little bit more than half. Okay. So a -0.6. Okay, in the next one, we're going to have -0.4. And our next one, we're going to have -0.2. We're still going to have 0 here. We're going to have -0.2, -0.4, and -0.6. Now, I am going to make my x's go just normally, okay? We're just going to go by 1s here. All right. But on my y-axis, each one of these, just so that we can see it a little bit better, is going to be going by 0.1. Okay, just so we can see it. But I'm labeling that so I know exactly what I'm doing. Now, the vertex is still at 0, 0. But when I go to my -3, I'm going to be down -0.6. And in my scale, that's 6. I had it 1 over. Sorry about that. We have each of our different squares being worth 0.1. So I'm 3 and down 6 to get to -0.6. Our next one, so -2, should be down 4. Okay, and here we go. So we can see, and it looks a little bit different because I have changed the scale, but we see that we still have kind of a different transformation here because of that negative 0.2. Now, to show you the compression, just to prove to you that this is truly a compression, if I were to do this and not change the scale at all, this is what it would look like. We would have our vertex right here. At 1, we would be at negative 0.2, so I'm barely going to be off the x-axis. At 2, I'm going to be at negative 0.4, so just under a half. And 0.6 is going to be just over a half. And I'm going to do the same on the other side here. Oop. There we go. Okay, so you can see how this is much more compressed than what we normally have with our absolute value function. That is a little bit more true to scale. Okay. All right, so we're going to end on this one. There's lots more examples here that I will just show and you can practice on your own. But let's just try this last one. A helicopter pilot is flying from town A to town B at 60 miles per hour to make sure he is on course. He will fly over a landmark that he knows is 20 miles from town A. Write and graph the distance from the landmark as a function of minutes of flight time. So we have lots of different information here. Now we can put it into this general formula for an absolute value function. We've looked at all of these things. The K is our vertical compression, or sorry, our vertical translation. H is our horizontal translation. And A is our constant here that either stretches or compresses. It's our dilation. So each of these, A is always going to be our rate, okay? Just like anything, the slope that we give something, the constant that we give something is always the rate. H we can talk about as the time from the landmark, and K is the closest distance to the landmark. So if we look at this, and I'm going to put this miles per hour into miles per minute, it's a little bit easier to see, and since we're talking about 20 miles, it might be a little bit easier to talk about it in how many minutes it takes to get there. So A is this rate, so 1 mile per minute. So I can plug that in and say f of x is equal to 1 times the absolute value of something. Okay, and h, that is the time from the landmark. Well, if it's 20 miles away at 1 mile per minute, it's going to take 20 minutes to get there. So I can say x minus 20. And then closest distance to the landmark, well, if I get to the landmark, I'm going to fly over the landmark. I'm going to be 0 miles away from the landmark, which means I have plus 0. So really what I am actually doing here is f of x is equal to the absolute value of x minus 20, which, like we've learned, is just a horizontal translation, and we are going to go to the right 20. And so you can see this is our absolute value function when we are done. Same slope, but we are looking at it a little bit different. Okay, it's just to the right 20. All right. Okay, here is another example here. Okay, a little bit simpler than the one right before it, and we really only care about that distance to the right in this one. Here are a couple more examples that you can practice graphing on your own. Just remember what H, K, and A represent in each of these so that you can make sure to graph them correctly. All right, well, I hope this is helpful for your homework and for studying.